Hello, this will be a demonstration of Proposition 18 from Book 8 of Euclid's Elements, which says that between two similar plane numbers, there is one mean proportional, and the plane number has to the plane number a ratio duplicate of what the corresponding side has to the corresponding side. This is quite similar to Proposition 8.11, but instead of just being restricted to two squares, which are a kind of two similar plane numbers, we're dealing with any two similar plane numbers. Before we get into that, I do want to refresh you all on what exactly similar plane numbers means. It means two numbers, which are the product of two other numbers, whose factors, as it were, are proportional. What that would look like here is we would have a proportion of C, D, E, and F, so that C is to D just as E is to F, and if we take the product of C and D, call that A, and we take the product of E and F, call that B, then the two numbers A and B will be similar plane numbers because their sides are proportional. Because C is to D just as E is to F, C times D, which is A, is similar to E times F, which is B. That being said, what we want to prove then is that between the two numbers A and B, which are two similar plane numbers, there is one mean proportional such that the number A is to this mean proportional, just as this same mean proportional is to the number B. And furthermore, that the ratio of A to B is duplicate of what C is to E or what D is to F. You look at our proportion, C to D to E to F. C and E are what we would call corresponding sides because they are both antecedents of this proportion. They fall in the same place of the two ratios. And D and F are likewise corresponding sides because they are both consequents of equal ratios. They're again in the same place of the two ratios. So A is going to have to be a ratio duplicate of what C has to E or of what D has to F. We're going to begin by noting that because the proportion C, D, E, and F is true, that C is to D just as E is to F, we can alternate this proportion by Proposition 7.13 and say that C is to E just as D is to F. That being said, we're going to create the number G. Number G will be the product of D and E. So D times E will make G. But you'll notice that the number D has been multiplied by the two numbers C and E to make two products, namely A and G. We know D times C makes A, that was given to us, and we know D times E makes G because that's how we made the number G. So the number D has been multiplied by two numbers to make two products, which then means by Proposition 7.17 that the two numbers multiplied have the same ratio as the products, so that C is to E just as A is to G. Well, remember, our first step was to say that C is to E just as D is to F. So we have two ratios which are the same with the same ratio, property of numbers. They are the same with one another, so that D is to F just as A is to G. Now, for the exact same reason, namely 7.17, we can say that D is to F just as G is to B. This would work because the number E has been multiplied by D and F to make G and B respectively. And we know from Proposition 7.17 that the two numbers multiplied are in the same ratio as the products, so D is to F just as G is to B. But remember, we just proved that D is to F just as A is to G. So again, we have two ratios which are the same with the same ratio, property of numbers. They are the same with one another, so that A is to G just as G is to B. And because this is so, the number G is a mean proportional between A and B. Because A is to G just as G is to B, which is the definition of a mean proportional. And we notice that there is exactly one between A and B. So that satisfies the first part of our enunciation. What about the second, about this duplicate ratio business? Well, that's quite simple, actually. Because A is to G, just as G is to B, we know that A has to be a ratio duplicate of what A has to G. This follows simply from the definition of duplicate ratio, which is the exact same as definition 5.9, all the way back from book 5, that if three numbers are proportional, continually that is, the first has to the third a ratio duplicate of what the first has to the second. So our first number A has to our third number B a ratio duplicate of what our first number A has to our second number G. Well, you'll remember in step 3, we proved that A is to G just as C is to E, and that A is to G just as D is to F. So you can simply substitute that ratio in for whatever that ratio is equal to by a property of numbers. So that A has to be a ratio duplicate also of what C has to E and what D has to F. And this is all we wanted to prove, which means we're done with the proposition, therefore, etc., Q, E, D. There is a lot to unpack about this proposition, both what are plane numbers, why exactly are they called plane numbers, what exactly is this duplicate ratio business? I mean, it should be similar to proposition 811, but it might play itself out differently because we're not dealing with squares. So let's begin unpacking that. First, what exactly are plane numbers? Plane numbers are simply a number that is a product of two numbers. So for example, 6 would be a plane number because it is equal to 2 times 3. We would also then call 2 and 3 the sides of 6, or as we would say nowadays, the factors of 6. And the reason we would call them plane numbers is, say we have a line that is too long, then we attach at a right angle a line that is 3 long according to the same unit. We can then complete the rectangle, as it were, by drawing more right angles. And the area of this rectangle will be the product of 2 and 3, namely 6. And you'll see that this is obviously a plane. It's also a rectangle, but it's a plane. And that's why you could call these plane numbers, because you can represent them as a plane contained by their two sides if you represent their factors or the numbers as lines. You can create a plane with the same area as their product. So then it should follow quite simply what exactly similar plane numbers look like and why they're called similar. Because they're called similar for the exact same reason that we would call rectilineal figures similar back in book 6, because they're equiangular and their sides are proportional. So let's draw that out. So 2 to 3, like that. That's an area of 6. But we can say double each of the sides and we will get a similar plane number. Because what will happen is we double 2, we get 4. We double 3, we get 6. We complete the plane like that, and the area of this will be 24. And what you'll notice is that these two rectangles, this smaller one to the left and this bigger one to the right, are similar because they're equiangular. The angles about them, or the angles in them, are all the same. They're all right angles, and their sides are proportional because 2 is to 3, just as 4 is to 6. So because the rectangles you can make out of these numbers are similar, Euclid calls plane numbers that have this sort of relationship similar plane numbers. It's the exact same reason he calls rectilineal figures similar back in book 6. So, that being said, I hope that's a decent enough explanation of what exactly similar plane numbers means, where the name comes from. I mean, plane numbers is kind of weird. We don't use that nowadays, of course. We preserve his language of square and cube numbers, but plane and, we'll see in the next proposition, solid numbers, that's fallen out of use, which is unfortunate because you lose the geometric intuition behind the name when you call them simply products. It's kind of unfortunate. Before I end the video, I always like to give particular numerical examples of what the proposition looks like if we play it out, so let's do that. So say we have a proportion of 4 is to 6, just as 8 is to 12. That's pretty easy to verify. They're both in a 2 to 3 ratio. 4 is to 6, just as 8 is to 12. So then, if we take the product of 4 and 6, and we take the product of 8 and 12, the two numbers so produced will be similar plane numbers because their factors, or as Euclid calls them, their sides, are proportional. So what's the product of 4 and 6? That's obviously 24. What's the product of 8 and 12? That's 96. And so because 4 is to 6 just as 8 is to 12, and 4 times 6 makes 24, and 8 times 12 makes 96, these are what we would call similar numbers, because you can represent them as rectangles, and the rectangles that you get will be similar rectilineal figures. So that's why these are similar plane numbers, of course. So, yeah, there's that. The first part of this proposition tells us that between two similar plane numbers, there is one mean proportional. What that would look like here is we would have 24 on one end, we would have some number, and the same number would have the same ratio to 96. It's a little off camera. I'm going to pack that in a little more, just so it's all on camera. Okay, so we want to find the mean proportional between 24 and 96. How we do that for Euclid is we take the product of the two inner terms, which are 6 and 8 here. So we put a 48 between here. And that's pretty easy to verify that 24 is to 48, just as 48 is to 96, because 24 is 1/2 of 48, and 48 is 1/2 of 96. So we see that the first part of this proposition holds. What about the second part? That gets a little bit more confusing, but I'll try to explain it here. What that part of the proposition says is if we take the ratio of 24 to 96, like that, you can represent it as a fraction, of course, that's not very controversial. This ratio will be equal to the duplicate of the ratio of the corresponding sides. What are the corresponding sides? Well, in the proportion, corresponding sides are either both antecedents or they're both consequents. So 4 and 8 would be corresponding sides, 6 and 12 would be corresponding sides, but 4 and 12 would not be corresponding sides, neither would 6 and 8, because they're situated differently between the two ratios. 4 and 8 are both on the left-hand side, and 6 and 12 are both on the right-hand side. So they would be corresponding sides. So the last part of the proposition tells us is if we take the duplicate of 4 to 8, we will get 24 to 96. So let's do that. Now, hopefully you'll remember what exactly it means to take a duplicate ratio. Arithmetically, it's equivalent to just squaring the ratio. So 24 to 96, I'm actually going to reduce that real fast. This would be a 1 to 4 ratio. 24 is 1/4 of 96. So like that. Now, 4 to 8, we can reduce that one as well to just a 1/2 ratio, because 4 is exactly 1/2 of 8. So if you square 1/2, you square 1 and you square 2. 1 squared is obviously just 1, but 2 squared is 4. So the ratio we would get if we square 4/8 will also be 1/4. 1/4 is obviously equal to 1/4, and so we see that the ratio of the two similar plane numbers, 24 and 96, is a duplicate of the ratio of the corresponding sides, namely 4 to 8, or you can do the same thing with 6 to 12. And you can do that with any proportion, any similar plane numbers. You can find their mean proportional, and you can check that the ratio of them is duplicate of the ratio of their corresponding sides or the corresponding factors. I hope that explains enough about what exactly is going on in this proposition, the language surrounding plane numbers, why they're called planes, why similar plane numbers are called similar, what exactly this mean proportional and this duplicate ratio business is. I hope I've explained that sufficiently. Now, with that said, I'm going to end the video here and move on to proposition 819.